In this example, we have a rectangular coil. It has total resistance R. It has N number of turns. We've got a length here, total W width here. The coil moves into a uniform magnetic field. It's moving with velocity V. Find the net force on the loop as it moves through the field. So as our loop starts to go into the field, it's going into an area with magnetic field pointing into the page. That's going to cause an induced field which points out of page. So there's our induced field. That's going to cause an induced current. The field comes out of page. Along the bottom, our current is going to the right. So it's going to cause an induced current that comes around like this. So our induced current is counterclockwise. So then on this segment of the loop, there's going to be a force, IL cross B. There's going to be a force that points to the left. So there's your induced magnetic force. The forces on the top and bottom would cancel. This would be a force that points up. This would be a force that points down. So our induced magnetic force is going to be to the left from our right-hand rule. So it's IL cross B, which is going to be minus ILB I hat. So we have to find our current. Current is potential over resistance. What is our potential? Well, our potential, let's see, I'll come up here. Potential is d phi dt, the magnitude of the potential. Phi is the net magnetic flux. The net magnetic flux is N times B times A. B and A are parallel, so we have NBA. A is the area of the loop, which is N times B times L times W. So W for the width of our loop in the field. So our induced potential then is d by dt of NBLW. NB and L are constants. So we're left with NBL dW dt. dW dt is how fast this is changing, so that's the speed. So this is our induced potential. We'll put this in for our current. That should be a V. We'll put this in for our force. We get minus N times B squared. B times B is B squared. L times L is L squared times V divided by the resistance R I hat. So our magnetic force points to the left. It slows it down. It resists it going into the field. When it's in the field, so as it's moving completely within the field, there's no change in magnetic flux. There's no change in magnetic flux. The induced field is 0 and the induced current is 0, so the induced force is 0. Okay? No force at all when it's in the field, so it likes being in the field and there's no resistive force at all. As it starts to come out of the field, we're coming from a region with lots of field into the page to a region with no field into the page, so the induced field is into the page. We ask, what current does that cause? Well, our fingers are going into the page, imagining we're grabbing the bottom part of the loop here. Fingers are into the page, thumb is to the left, so the induced current comes around this way. What direction force does that give? Your thumb goes with your current, your finger goes with your field, your middle finger shows your force, points towards the left. So the induced magnetic force is to the left. So our B induced is into the page. Our I induced, this time it's clockwise. And our induced magnetic force is IL cross B, same equation. Force is to the left, so it's going to be minus ILB I hat. Current is potential over resistance. Our potential is going to be the change in flux over the change in time. Our expression for the flux is the same, so the potential is the same, so the current is the same. So the magnetic force is exactly the same. So that's kind of interesting that it also slows it coming out of the field. So the magnetic force is resistive to change, so it resists going into the field. It's okay while it's in the field, and it resists coming out of the field. That's kind of an interesting application.